Enabling the voice mix. Just enabling the voice mix. Hello. Here we are talking about laminar flow for nuclear reactors. And we are considering steady state fully developed flow. And in two prior videos, we derived the cylindrical coordinates momentum equation, and we derived the velocity profile in a circular tube along with the mean velocity in a circular tube for laminar flow, steady state, fully developed. And in this video, we will calculate the pressure drop by using the velocity profile along with the friction factor definition, so that we can find a value for the pressure drop across a horizontal flow in a tube. And what we can do is start off where we left off last time. So we have an equation for the velocity profile as a function of r in a tube, and we have the mean velocity for the flow in that tube. And what we found is that the velocity profile, which is a parabolic shape as described in that first equation on the left, is a maximum in the center of the tube, and then it's zero at the walls due to friction with the wall. So this is the velocity profile as a function of r, the radius. And we found it interesting, or I made a note that I think you should note as interesting, that the mean velocity profile in this tube is half of the maximum velocity. So the maximum velocity is in center. The average or mean velocity across the entire cross-sectional area of this tube is exactly half of the maximum. And I noted in the last video that we saw the same behavior for the temperature in a cylindrical fuel pellet, where the centerline fuel temperature, I should say, the difference between the centerline fuel temperature and the temperature at the outside of a fuel pellet can be found. And then once you have the centerline temperature and the outer temperature of the fuel pellet, the average temperature of that entire cylindrical pellet is half of the maximum temperature, is halfway between the fuel pellet temperature at the outside of the fuel and the fuel pellet temperature at the center line. Okay. In this particular example now, we have the equation for the velocity profile as a function of r, and the equation for the velocity, for the mean velocity, both dependent on dp dz. So we can solve this equation for the mean velocity in terms of minus dp dz. So we end up with minus dp dz is going to be equal to mean velocity times 8 mu times 1 over r squared. And then we can take this result and put it into the pressure gradient in the velocity profile equation, and we end up with this result. It simplifies to show that the velocity profile in the radial direction is 2 times the mean velocity times 1 minus r squared over r squared. And we can check this to make sure that we understand it. If we plug in r equals 0, then I will have the, that's at the center line of the tube. If this becomes 0, then 1 minus 0 is 1. And I end up with the velocity at r equals 0 is twice the mean velocity, which is what we'd expect. I plug in r equals r, which is at the wall. I should expect that the velocity is 0 at the wall due to friction of the fluid with the wall. And indeed I find that if I plug in r equals 0, the wall radius here, I have capital R squared over capital R squared. 1 minus that gives you 0 for the velocity at the wall. Okay. So, next we want to apply the definition of the shear stress at the wall and relate that to the mean velocity. So shear stress is defined as viscosity times the velocity gradient. So we have, in our case, we have viscosity, and in our case our velocity gradient, our velocity is only in the z direction, so we have a v velocity that's varying with r, and we can take this result and apply it to our mean velocity. So first let's take the derivative of our velocity profile from our last slide, shown here, right here, this equation. And if we take that equation and take the derivative of it, we get minus 4 times the mean velocity times r over r squared. So let's take this value and plug it in right over here to the derivative of the velocity with respect to r. And if you do that, you get that the shear stress at the wall, where the fluid is contacting the wall, is minus 4 times the viscosity times the mean velocity over r. And then we also had on our last slide that the mean velocity is equal to r squared over 8 mu times pressure gradient. So if we take this result and put it in to Vm, we then end up with the wall shear stress being proportional to the pressure gradient times half the radius. So we've related the shear stress at the wall to the pressure gradient. Then we can apply the definition of the friction factor. So the friction factor definition is related to the pressure gradient, and in our case here the pressure gradient has to do with the mean velocity squared over 2 times the density. So the higher the density, the greater the pressure gradient. And then we have the friction factor over the diameter. So the diameter is inversely proportional to pressure gradient, friction factor directly proportional to gradient, density proportional to pressure gradient, and that pressure gradient proportional to the velocity squared. Now if we take this friction factor, the pressure gradient from the friction factor definition, and we take our friction factor from the shear stress equation, and we take our pressure gradient that we just solved for in the shear stress equation. On the last slide we got this. This is our result from the last slide. Then we can solve for the shear stress at the wall in terms of the friction factor. So what we've done is just taken, we've taken this equation here and plugged it in over here. And then you simplify with the diameter and the radius being related to each other by a factor of 2, and you get that the shear stress at the wall is proportional to the friction factor over 4 and rho v squared over 2, which is a kinetic energy factor, or kinetic energy of the flow. So now we have wall shear stress defined in terms of the friction factor and the mean velocity. So we can solve for the friction factor by combining that friction factor definition from the last slide, right here, and our mean velocity, which is right here. So each of these two equations have the same term on the left side, so we can equate the right sides of these two equations. We can equate the friction factor term as related to the pressure drop to the mean velocity as related to the pressure drop. And solving for that gives us the friction factor is 64 divided by rho dV over mu. And this term at the bottom we should recognize as the Reynolds number. So the friction factor is equal to 64 of the Reynolds number for laminar flow in a horizontal tube. And we can use that fact to solve for the friction pressure drop for any given pipe length, because we have a pressure gradient defined in terms of a friction factor and a friction factor defined in terms of the Reynolds number. So if we're going to solve for our friction, we're going to take our pressure gradient and integrate along the length of the tube. So to understand what this equation means, I've got a tube and I've got fully developed flow in it, and we'll assume that we have Z in over here and Z out at the far end. And what we will do is integrate along that length of tube L for the pressure gradient, given the fact that we have this velocity profile and this friction factor operating in order to cause that pressure gradient due to the wall. Excuse me, in order to cause that velocity profile due to the wall drag on the wall. So in short, what we did is we took our pressure gradient in the z direction. We took that equation from the last slide which is right here. Just took this term and integrated it from 0 to L. And that's what we get. So now we can calculate the friction factor. We can calculate the pressure drop for a certain length of tube if we know the average velocity of the fluid, the size of the pipe, the density of that fluid, and the friction factor, where the friction factor is going to be defined as 64 over the Reynolds number, as defined here. And that's it. Thank you.